Hola, hola. Bueno, chicos, ayer, mientras no estaba streameando, terminé todo lo que es el CPU. Pero el CPU, la verdad que era bien sencillo. No, perdón, el hack computer. El CPU fue lo más difícil que hicimos, la verdad. Y terminamos el computer, que en realidad es bien sencillo, siguiendo el diagrama que dieron. Pero no lo grabé. Igual funcionaron bien todas las pruebas. Así que hoy vamos a ir a la semana 6. Claro, y aquí uno se pregunta cómo habrá sido el primer compilador, ¿no? Si no tenía un compilador, ¿cómo habrán creado el primer compilador? ¿Cómo compilaste el primer programa? Y la respuesta supongo que es que usaron papel y lápiz, ¿no? Como está diciendo acá. Igual el proceso de compilación no es muy complicado si las reglas son tan simples, ¿no?
Last week, we've built a computer that can run code, machine language code. 2 weeks ago, we've actually programmed in machine language, but we didn't really program in binary code, but rather in assembly language in some kind of nice syntax. So there is a gap in the middle, and the gap is supposed to be a simple software program called an assembler. So specifically, you've seen this slide already twice. 2 weeks ago, you've seen this slide to focus on the left-hand side, on the actual assembly language format in which you were supposed to program. That was your perspective 2 weeks ago. Your perspective last week was what happens on the right-hand side, the machine language, since you had to actually construct a computer that can actually execute the ones and zeros that you see on the right. Our focus, our perspective this week is going to be in the middle. How do you go from left to right? How do you do from left to right? How do you do the operation, the assembly operation? I.e., what is the assembler, which is a program that translates what you have on the left, the assembly language code, to what you have on the right, the machine language code. Now notice that for the first time in this course, this is software. This is going to be a program that takes as input a file written in the left hand side format, i.e. in assembly language, and produces another file that's written in the right hand side format, i.e. Zeros and ones, which directly can be executed in a computer. So this is a software, the first time that you do software in this course, until now it was always hardware. And it's really the first software layer the first software layer that basically we have in every computer. There's much more software above it, but this is the first level, and we're doing it together with the hardware to give us a complete picture. So we can have a computer that we can understand how you program it, and understanding how you program it does not mean programming it in 0 and 1s, but rather in assembly language, which is still a very, very low format, essentially equivalent to machine language, but still it's something that humans can relate to. So let's see what kind of software is this going to be, this assembler. In principle, we've only created a computer that can run machine language code. So in principle, we should write our program in the only language that can be directly executed, i.e. in machine language code in 0s and 1s, which is going to be pretty annoying. But the best way to think about it is that we're not constructing the first computer in the world, but rather the second one. So let us assume we already have a computer that can run some high-level language. In particular, I'm talking about your computer and the high-level language that you already know. So we're going to write the assembler in that language, and it will be a software program that runs on your computer. What it's going to produce, the machine language that it's going to produce, is machine language for the hack computer, for a different computer, the computer on which you will actually run the produced program. So we're thinking about a cross-compiler, sometimes it's called. It's running on one computer and producing code intended for another computer. This way, we don't have this loop, we don't have this bootstrap problem of having to write our assembler in machine. It's running on one computer and producing code. It's going to produce, the machine language that it's going to produce is machine language for the hack computer, for a different computer, the computer on which you will actually run the produced program. So we're thinking about a cross-compiler, sometimes it's called. It's running on one computer and producing code intended for another computer. This way, we don't have this loop, we don't have this bootstrap problem of having to write our assembler in machine code, but rather we can write it already in the high-level language that we've already implemented on another computer. So the assembler program is really a very simple program. It does the following basic loop and repeats it again and again. It reads one assembly language command from the input. It basically breaks it into its parts, and each one of its parts can be translated to binary in a unique way that's specified by our language. And then we take the binary code of the different parts put them together, and we get the machine code that directly is equivalent to the assembly language command that we just read. We output that, and we move on to the next assembly language command. We keep on doing that and translate one command after another without having to remember anything that happened in the history. Very simple. So let's look at the different stages, each one of these different stages, slightly more carefully. So how do we read the next assembly language command? Well, it seems that we just read the next line from the input. This is almost exactly what we do. The only other difficulty is that we may need to skip what's called white space, for example, comments. We need to make sure that we read what is really the next command and not any kind of a comments or any type of spaces or blank lines that are read there. So when we read it from the file, we have a file that, let's say, has a command load R118, and this is just a fictional language, assembly language. Later, in the next unit, we'll start actually talking about the hack language specifically, but in this unit, I'm still focusing on a generic assembler program. So let's assume that our hypothetical assembly language has this type of command, load R118, which we expect would probably mean taking the value 18 and putting it into the first register. But this is not something that we need to know when we're actually doing this translation. We actually want to read that command and put it into some kind of string variable, into some kind of array of characters that we can later work on. And that is basically what's involved in reading a line by line from the input. So the next step is taking this string of characters and breaking it into its different parts. So when we look at it, we see that the different parts of this command are load, first part, R1 should be the second part, 18 should be the third part. Each one of them has meaning, and there's also a space and a comma, but these are not really the interesting parts of the command, but rather just some syntax which helps us break and understand what's written, the important part in the command. So the next thing we have to do is basically understand the syntax and break the original string into these three different, if you wish, substrings, the three different interesting parts that are involved in this command. So that involves basically some kind of simple string manipulation until we get the different parts. Once we have these different parts, then we will need to translate each one of them to machine language, to actually its binary counterpart. Now, how do we do that? That has to be part of the specification of the machine language and assembly language. Basically tells us what is the code for each one of these commands, for example. So for example, the load command, we would probably have some kind of table which tells us what is the machine language code for each command. In particular, we can look up in that table and see what is the machine language code for the load command. Other parts of the input may be, for example, numbers, or maybe other things that we can directly translate into machine language just because they are number. For example, the number 18 may be translated into the binary representation of the number 18. Again, this is part of the language specification. This is a basic part. This is the part where we need to understand exactly the mapping between assembly language and machine language, which is usually very simple and specified completely by a bunch of tables and a bunch of rules of where you put integer numbers in the binary form, and that's about it. The third part is now we have basically the translation of each part of the input, and we need to put them together. Usually it's just some kind of concatenation. Maybe we will need to put also some kind of other bits that are defined in the specification to actually pad them and complete the language, because sometimes the translation of a command does not fill all the available bits that are available in the machine, and the other bits are specified to be some, let's say, a constant 0 or 1. So now we have basically the number the binary number that we need to output, and we just need to print it out into some kind of file. How exactly we print it out is according to, there's going to be some kind of specification of the file format of machine language, which may be a binary format, which may be just in characters 0 and 1, that would be not something that you would usually have, and so on. But then you just need to basically translate the numbers you have in your memory, the ones and zeros you have in your memory, you have to translate that into a format that the machine language can actually, that the computer can actually execute. So far, we've described the basic operation of the assembler, and now there's one extra complication that we need to worry about, and that is symbols, handling symbols. As you may recall, one of the major services that an assembly language gives a programmer is the ability to use symbols rather than direct numbers. And we usually use them for two different types of things. One of them is for labels in the program. To jump into a certain part of the program, you give it a name rather than really hard code the address, and the other is you want to give a variable a name rather than always refer to its exact address in memory. So for example, we can write in most assembly languages jump loop, and loop is going to be translated automatically into some kind of address. Similarly, we can load into a register a variable weight, and again, weight is going to be some location in memory, which the assembler needs to figure out which location and will basically translate this access directly to accessing that location in memory. So basically what our assembler will have to do is replace each one of these symbols, for example, the weight in the previous command, into its equivalent address, and it will have to remember where exactly is that address in the memory. Similarly, it will replace the label of a loop, of a jump, with the exact address inside the program, and again, remember where that is. How does that happen? How will that be done? Well, it will need to maintain some kind of a table that basically has the information about the translation between symbols and actual addresses. And whenever it needs to do this translation, it will have to actually look up in the table. It sees weight in the assembly language program. It will have to look up in the table and see what is the correct address to put instead of it. Once it's replaced the symbol with the address, then it can continue as we previously described. So let us see now, how do we maintain such a table? How do we enter information into it, and how do we look up information from it? So for example, let's say now our assembler is reading command by command, and it encountered this command with a variable weight in it. So maybe the variable is already in the table. We need to look it up in the table. If it's already in the table, then we know exactly how to translate it. This is the easy part. But what happens the first time we see this variable weight? Well, we look at it, we look in the table, and we see that it's not there. So we know that we need to allocate a new memory location to hold this variable. And this is one of the things that our assembler will have to do. So it will actually find the next memory location that's available. And the exact definition of where does it allocate memory addresses should be part of the assembly language specification. And it will basically allocate this new memory to this symbol. And now it has this pair of symbol memory address that it can put into the table and use from now on, including for now. And this is how basically we put variable locations into the table and how we use them. The other kind of symbols that we have are labels. So let's say let's say for example we have a piece of code that has in it a label loop. What does this mean? When our assembler actually looks and reads this line label, it knows, well, this is just a label. It's not a real command to execute, but I have to remember that the next time somebody wants to jump to this symbol loop, I have to remember where exactly it is. Where is it? Well, I have to remember what address is the current command going to be put into the memory, and that is going to be the address that's referred to by loop. So for example, if this current piece of program is being allocated being written into memory locations 671, 672, 673, and so on of the program memory, when we see this label, our assembler will have to remember, the next program is program 673, so I need to remember that loop from now on always refers to location 673. Of 671, 672, 673. And that is going to be the address that's referred to by loop of code that it can put into the table and use from now on, including for now. And this is how basically we put variable locations into the table and how we use them. The other kind of symbols that we have are labels. So let's say for example we have a piece of code that has in it a label loop. What does this mean? When our assembler actually looks and reads this line label, it knows, well, this is just a label. It's not a real command to execute, but I have to remember that the next time somebody wants to jump to this symbol loop, I have to remember where exactly it is. Where is it? Well, I have to remember what address is the current command going to be put into the memory, and that is going to be the address that's referred to by loop. So, for example, if this current piece of program is being being written into memory locations 671, 672, 673, and so on of the program memory, when we see this label, our assembler will have to remember, the next program is program 673, so I need to remember that loop from now on always refers to location 673. And this is basically the kind of thing that it needs to do. And then when we actually get to a place that uses this label, uses this symbol, then we already have in our table what exactly is the correct address. So that's basically how information about labels is put into the table and read from it when needed. Now there's one extra complication that we didn't talk about, that sometimes we can jump into a label before the label was actually defined. This is called a forward reference. So for example, it's very common in programs that I will need to jump, let's say, into a label called continuing, cont, before the label actually occurred in the program. If that is the case, when I reach the first jump, the jump instruction that uses a label, that happens before I've already seen the place that defines a label in the label command, and how can I handle that? Because it's not in the table yet. Well, there are two ways to handle it. One way, which is usually a little bit more complicated, is to basically remember that I've seen a label that I don't know where it is yet, keep it in a side table, and when I actually get into the definition of the correct address, fix it back. Another option, which turns out to be sometimes easier, is that I actually do everything in two passes. In the first pass, I read everything only paying attention to the labels and remembering where each label refers to. That's when I actually build the table for the labels. And only in the second pass do I actually go and put and convert each and every label into its correct code, into its correct address that now is already in the table because I put it there in the first pass. And that's usually slightly easier to do, but you may use each one of these two possibilities. So now we finished talking about the general process of creating an assembler, the general thing that an assembler must do. And what we're going to do in the next few units is start talking specifically about the hack machine assembler and talk about the different parts of how you actually construct it. In the previous unit, we talked about the assembly process and logic in general, and about writing assemblers in general. And in this unit, we will start the journey of actually building an assembler that works and that can translate programs from symbolic hex code into binary hex code. So here is the overall picture in a nutshell. We are given a source program written in symbolic hex language, and we have to translate it into an equivalent program written in binary code. So if you were the person who is supposed to write or to develop such an assembler, how would you go about it? I mean, what is the knowledge that you have to know in order to develop such a general purpose translator? Because bear in mind, we have to be able to translate any program written in hex symbolic code, not just a subset of programs, but any given program. Well, this is, in general, it's a translation challenge, right? You have to translate from one language, from the source language to the target language. And in order to do this, you have to know the grammar of both languages. You have to know the syntax rules. For example, if you want to translate from French to Spanish, you have to know the grammatical rules of French in order to take the source sentence and decompose it or parse it into its lingual elements. Then you observe or you inspect these elements, you figure out what is the semantics of this sentence, and then you re-express this semantics in Spanish. And in order to do this, you have to know the rules of the game in Spanish. You have to be able to synthesize a target sentence written in the target language. And that's exactly what we do here. However, when we write translators for programming languages, the task is supremely easier because programming languages are supremely simpler than human spoken languages or natural languages. And in particular, machine languages are very simple, and therefore the translation task is going to be less formidable as it may seem at the outset. All right, so what do we have to know about the hex language? Well, the hex language consists of A instructions, C instructions, and symbols. So let us explore every one of these categories very briefly. The A instruction comes up in its symbolic syntax, and here is the equivalent binary syntax. And if you want to translate one to the other, I think it doesn't take too much imagination to figure out how to do it. And in any rate, we're going to say it explicitly down the road. The C instruction, in a very similar fashion, has a symbolic syntax and a binary syntax. And there's a set of tables that describe the mapping between the former and the latter. And finally, the hex language features symbols. You know, the programmer is invited to use some predefined symbols, and also the programmer is invited to invent symbols of his or her own using the label declaration statement and eth statements or A instructions that are designed to declare and use variables. So this basically, this is a complete description of the hex machine language, and given this description, you should be able to develop the desired assembler.
So given that we have a program in which all these things that I mentioned before come to play in a vivid example, what exactly do we have here, in terms of general constructs? Well, first of all, we have white space. We haven't mentioned white space in the language specification. We should have, but the white space is almost the same in every language that you can think about. You are welcome to introduce empty lines and comments. And in the Hack language, a comment is anything that begins with 2 slashes. So we have to know how to deal with white space. And then we have a sequence of A instructions and C instructions that we have to translate. And finally, we have to deal with the symbols. Symbols come to play either in label declaration commands or in references in the context of A instructions. So to make a long story short, if you want to write an assembler, you have to know how to deal with white space, with instructions, and with symbols. Let me say a few words about symbols before we go along. I've used red ink in what you see here in order to highlight all the symbols that appear in this program, and as you can see, there are quite a few of them, and that's quite characteristic to symbolic machine language programs. They have numerous symbols in them. So the question is, how do we deal with these symbols? Well, the answer is that in many cases in life, when you face a big mountain in front of your track, well, in some cases, the best way to deal with this mountain is simply to bypass it, and that's exactly what I'm going to do with the symbols. I'm going to deal with them later. And by the way, if we are lucky, as we bypass this mountain, we may gain some ground, and then summiting the mountain may be easier from the other side than from the original side. And indeed, you will see that when we'll introduce symbols later on in the process, it will be much easier to morph them, so to speak, into our assembler solution. All right, so symbols later. And with that in mind, I now have to deal only with programs that have no symbols. And the assembler that I have to write is much simpler. It's an assembler that deals with symbol-less symbolic Hack programs. So the challenge that remains is to deal with white space and instructions only. And let us begin with white space. What should we do with white space? Once again, I've used red ink to highlight all the white space in the program. And the easiest way to deal with white space, and obviously the most sensible way, is to simply ignore it. So as you process the source code, whenever you see a comment or an empty line, you simply toss away all the contents that follow in this specific line, and you go on to translate the remaining code. So white space is simply ignored. So what remains after we eliminated the white space is only instructions. So the challenge is reduced to translating programs that have pure instructions, so to speak, and this is a sequence or a stream of A instructions and C instructions, and in order to translate them, we have to know how to translate these instructions into binary code. And that's exactly what we're going to do in the next unit. But before we introduce the next unit, I'd like to give you an overall picture of where we're heading from here onward. Well, here's the plan. Since we decided to defer the treatment of symbols to a later stage, we'll begin by writing a basic assembler that can deal with programs that contain no symbols. This will be done in the next unit. In the subsequent unit, we are going to develop the ability to represent, handle, and use symbols. And finally, using this ability, we're going to return to the basic assembler that we wrote before and morph it or extend it into a general purpose assembler that can translate any given program, any given program written in Hack assembly code into binary code. This is the plan. So beginning with the next unit, we're going to talk about how to translate instructions. Writing a basic assembler that can deal the challenge is reduced to translating programs that have pure instructions, so to speak, and this is a sequence or a stream of A instructions and C instructions, and in order to translate them, we have to know how to translate these instructions into binary code. And that's exactly what we're going to do in the next unit. But before we introduce the next unit, I'd like to give you an overall picture of where we're heading from here onward. Well, here's the plan. Since we decided to defer the treatment of symbols to a later stage, we'll begin by writing a basic assembler that can deal with programs that contain no symbols. This will be done in the next unit. In the subsequent unit, we are going to develop the ability to represent, handle, and use symbols. And finally, using this ability, we're going to return to the basic assembler that we wrote before and morph it or extend it into a general purpose assembler that can translate any given program, any given program written in Hack assembly code into binary code. This is the plan. So beginning with the next unit, we're going to talk about how to translate instructions. In this unit, we're going to talk about the challenge of translating individual statements or individual instructions from symbolic to binary code. Now, the general problem that we are facing is developing an assembler that translates program from symbolic Hack language into binary Hack code. And in order to write such an assembler, we have to know how to deal with white space, instructions and symbols. Now, in order to make our life easier, we decided to defer the treatment of symbols to a later stage, and we also described previously how to handle whitespace. Basically, we're going to ignore whitespace, so what remains is a program that contains instructions only, A instructions and C instructions, without symbols. So in order to write an assembler that can translate such a program into binary code, we have to know how to translate A instructions and C instructions, and that's exactly what we're going to discuss next. So let us begin with A instructions. Here's the general rule and the syntax rule of how to put together an A instruction and an example. And here's the same instruction expressed in binary code. Notice that the opcode of an A instruction is 0 binary code. Notice that the opcode of an A instruction is 0. This is the first red 0 bit that you see in the example at the bottom right. By the way, the colors are completely meaningless, and I use them only to improve our communications. Once it gets into actual implementation, the colors once again play no role whatsoever. So how to translate from symbolic to binary when it comes to an A instruction? Well, if you think about it, the only challenge is to do something with this value. So basically, if the value is a decimal constant, all we have to do is compute the binary representation of this value, add as many zeros as we need in order to turn it into a 15-bit constant, add or append the 0 opcode, and that's what is needed, a 16-bit representation of this instruction. So it's not a big deal, but obviously we have to do it. What if value is a symbol? Well, I just want to remind you what we said earlier. We're going to deal with symbols later on. So translating instructions is something which is not terribly complicated, but once again, it takes some programming. All right, what about C instructions? Well, C instructions also have a symbolic manifestation and a binary manifestation, and there's a set of tables, so to speak, that describe the mapping from symbolic mnemonics into their binary representations. So these are the rules of the game when it comes to translating C instructions. So how do you actually do it? I think the easier way to describe the translation process is to do it using an example. So suppose we are giving this single C instruction, and we have to translate it into binary code. Well, before we go on, I want to remind you that every C instruction consists of 3 fields. So in the example that we have here, the MD mnemonic is the destination field, or the value of the destination field in this particular instruction. Then comes D+1, which is the value of the comp or computation field. And we also have a jump field, which happens to be null. We don't have a jump instruction here, so the jump is null. So implicit in what I'm saying is the assumption that we can somehow take this source instruction and decompose it into these 3 fields. And indeed, this is something that is going to be done by an element of our assembler called parser. The parser is going to take a source statement or instruction written in a symbolic code and chop it into 3 individual fields, and then we can inspect every one of these fields in isolation and act on it. And that's exactly what I'm going to do next. So let us begin to put together the string of characters that will end up representing the binary code of MD equals D+1. We can do it in many different ways, and here is one of them. Focusing on the target expression, we see that every C instruction begins with 3 1s when it comes to the binary flavor of C instructions. So we initialize the string that we're building with 3 1s. That's what we do when we get started. Next, we focus, if we want, we focus on the next 7 bits that we have to create. And these 7 bits correspond to the comp field. Now, the comp field happens to be D+1. Once again, I assume that I have access to this field. I can easily retrieve it. I see that it's D+1. And if it's D+1, I can look it up in the relevant table. I look up this mnemonic, and I see that it corresponds to an A bit, which is 0, and to 6 control bits, which are 0 and 5 1s. So putting these bits together, I generate the 7-bit value 0, 0, 1, 1, 1, 1, 1, and I append it to the string that I gradually build here. All right, the next thing to do is focus on the next part of the instruction, which corresponds to the destination. So I look up the value of my destination field. It happens to be MD. I consult the relevant table, and I see that the MD mnemonic corresponds to 0, 1, 1. I take this 0, 1, 1 value, I append it to the string that I gradually build, and I've completed the synthesis of these two fields together. Moving along, the remaining 3 bits correspond to the jump directive. I look up the value of the jump directive in my source instruction. I see that it's null. I look up null in the relevant table, and I see that it corresponds to the 3 bits 0, 0, 0. I take these bits, append them to the end of the string, and voila, we have managed to translate the symbolic instruction into its binary equivalent. As you see, everything that I do here is text processing, and in some languages it is called string processing. I have a source string, which I analyze in some way, and I have a target string, which I build, in some gradual process. And every high-level language has the capability to do such a string processing, and that's exactly what you'll do when you actually write the assembler. Now, when we say that we generate binary code, the languages it is called string processing, bits 0, 0, 0. I take these bits, append them to the end of the string, and voila, we have managed to translate the symbolic instruction into its binary equivalent. As you see, everything that I do here is text processing, and in some languages it is called string processing. I have a source string, which I analyze in some way, and I have a target string, which I build, in some gradual process. And every high-level language has the capability to do such a string processing, and that's exactly what you'll do when you actually write the assembler. Now, when we say that we generate binary code, there may be some misunderstanding here, so let me clarify it. We basically generate a text file that contains which consists of 2 characters only, 0 and 1. But they are treated as characters, as ASCII or Unicode characters. So we have this text file that we write, which consists of 0s and 1s only, and later on we're going to load this text file into the computer. And once we load it into the computer, it becomes real 0s and 1s, so to speak. All right, so this basically concludes the translation of C instructions. So with that in mind, here is the overall assembly logic. We are given a text file, and this text file contains all sorts of characters that hopefully represent a hex program written in symbolic hex code. So how do we translate it into binary? Well, we process this file, and we begin marching through it, and for each instruction, or for each line in this file, we first of all parse the instruction. We break it into its underlying fields. So if we have an A instruction, we have the @ sign and a value. We take this value and we re-express it in binary code. If it's a C instruction, we split the instruction into its 3 fields, comp, dest, and jump. And also, for every one of these fields, we generate the corresponding binary bits, and then we assemble all these codes that we created into a single 16-bit instruction, and we write this instruction to an output file, which is not seen here in the picture, but the assembler creates this empty file at the beginning and begins to populate it with lines, each line being a sequence of, or a string of 16 zeros and ones. So this is the overall process of translating a hex program, a program that consists of only A and C instructions without symbols. If you do all this, then you will manage to create an assembler that can translate programs into binary code, and everything looks very nice indeed. And I'd hate to be a party spoiler, but there's a big gap that we haven't closed yet, and this is the fact that the source code contains no symbols. We have managed to design an assembler that translates symbol-less programs, but we still have to close this gap of dealing with symbols. And that's exactly what we're going to do in the next unit. In this unit, we will talk about how the assembler represents and handles symbols using binary code. So the general problem that we are facing is writing an assembler for the HEC machine language, and the development strategy that we adopted was one of delaying the treatment of symbols to a later stage. Well, this later stage has come up, and we now have to deal with symbols explicitly. I want to remind you that we already know how to handle whitespace and instructions, and therefore we now want to focus on symbols. And as usual, I use red ink to highlight all the symbols in this particular example, and as you can see, there are quite a few of them. And I think I mentioned it before, this is very typical in programming in general and machine language programming in particular. The more symbols you have, the more expressive and easy to read is the program, and therefore we encourage programmers to use symbols, which means that the assembler has to work hard to resolve these symbols into binary code. But once we do it, we achieve something very remarkable, because symbolic programming is a very nice abstraction that improves the quality of your program and the quality of life of the programmer significantly. Okay, so what kind of symbols do we have in HEC programs? As it turns out, they fall into three distinct categories. First of all, we have variable symbols. Variable symbols represent memory locations where the programmer wants to maintain some values that typically change in the course of executing the program. Now, this sentence is a little bit misleading because the programmer doesn't care at all where these variables are actually located in memory. As far as the programmer is concerned, he or she is going to say something like at sum or at x or at y, and let the assembler worry about where to store these or represent these variables in memory. Once again, this is a very nice abstraction that the assembler delivers to the practicing programmer. So this is one kind of symbols we have to worry about. Another kind of symbols is label symbols that represent destinations of go-to commands in plural. And in this example that we are facing here, we have three such symbols: loop, stop, and end. And finally, we may have all sorts of predefined symbols like virtual registers, screen, keyboard, and so on and so forth. And in the example that we have here, I think we have we happen to have two predefined symbols, which are R0 and R1. So if you want to deal with symbols, these are the three kinds of symbols that you have to handle. So let me begin to describe what to do with every one of these symbols, and we'll start from the end. We'll start with predefined symbols. So according to the HEC language specification, the language features 23 predefined symbols, and here you see all of them. And how do you translate such a symbol into binary code? Well, first of all, we have to realize that these symbols come to play only in the context of A instructions. So the only place where you can see such a symbol popping up in a program is an instruction like at predefined symbol. How do you translate this instruction into binary? Well, you simply replace the predefined symbols with its corresponding value, which is a decimal number. And now the only thing that remains is to translate the at decimal number into binary, and this is something that we discussed in the previous unit. So case closed. We know how to handle predefined values. The next category of symbols that we have to deal with are symbols that denote labels. Now, label symbols are used to denote destinations in the program that I may want to jump to using goto commands, and they are declared very specifically using the pseudo command round parentheses and the name of the label in the middle. I've used XXX to stand for this label, which can be any sequence of characters. And these things are called pseudo commands because they don't generate any code. When we translate the program into binary, we don't translate the label declaration instructions, and that's why they're called pseudo commands, and we'll talk about this further later on. So we declare label symbols using the agreed upon parentheses, and you might ask yourself, why parentheses? Why not label colon or something like this? Well, when Noam and I designed this language, we decided to use this syntax, once again for reasons that will become clear later on. Now, once we declare a symbol using round parentheses, the meaning of this declaration is that from now on, whenever we see XXX in the program, we mean to replace it with the address of the memory location that contains the next instruction in the program. Now, in order to make sense of what I just said, I have to keep track of instruction numbers, and that's what I do next. If you look at the left-hand side of the slide, you will see that I have marked or labeled every instruction in the program with a running number that starts with 0. And notice that I'm skipping empty lines. Empty lines are white space, which is tossed away. And also, I'm skipping the pseudo instructions. So label declaration instructions like loop, stop, and end are not counted, so to speak. Now, once I have these line numbers in front of me, or once I remember it somewhere in my memory, now I see that I can relate loop to the number 4, stop to the number. I have these line numbers loop, stop, and end are not counted, so to speak. Empty lines are white space, which is tossed away. And also, I'm skipping the pseudo instructions. So label declaration instructions like loop, stop, and end are not counted, so to speak. Now, once I have these line numbers in front of me, or once I remember it somewhere in my memory, now I see that I can relate loop to the number 4, stop to the number 18, and end to the number 22. So I can basically generate this association and keep it in the back of my mind. So from now on, whenever I see an instruction like at loop, we actually mean at 4. We want to go to instruction number 4, and so on and so forth for all the other label symbols in your program. So how do you deal with an at label symbol instruction? Well, all you have to do is look up the value of this instruction, which you figured out before, as I just explained, and replace it with the symbol. What remains is an at value instruction, where value is a decimal number, and we know how to deal with this because we discussed it in the previous unit. So that's how you deal with symbols that represent labels. The last category of symbols that we have to deal with are symbols that represent variables. Now, as you recall, when you wrote programs in the hex symbolic language, we have this fantastic ability to create and use as many symbolic variables as we want. This is one of the most important abstractions in programming. And someone has to pay the price, so to speak. Someone has to implement this abstraction. And as you can imagine, the agent that implements this abstraction is the assembler. How do we do it? Well, according to the hack language specification, any symbol that appears in a program which is not predefined and is not accompanied by another label declaration statement is considered a variable. We have two such variables in the example in front of us, and they are called I and sum. And the program, as you can see, begins with 4 lines of code that basically declare and initialize these two variables to 1 and 0 respectively. It's not terribly interesting, but I'm just trying to add some color to this discussion. All right, so we know how the programmer expresses variables in the way that I just described. How do we handle these variables if we are the assembler? Well, each such variable is assigned a unique memory address starting with 16. You may ask yourself, why 16? Well, this is a decision that Noam and I made when we developed this language and this assembler. And it's not exactly an arbitrary decision, as you will see later on, but for now, you can treat it as an arbitrary decision. So variables are assigned to memory from address 16 onward. All right, so with that in mind, we have only 2 variables in this program, I and sum, and the values of these variables are going to be 16 and 17. Now, like any other symbol in a hack program, the only context in which such symbol can come to play is in the context of an A instruction. So we may see instructions like at variable name. We definitely will see them because otherwise, why did we declare these variables to begin with? We want to act on these variables, and we do it using A instructions followed by C instructions. So whenever we see such an instruction, how do we translate it? Well, all you have to do is the following. If you see this instruction for the first time in the program, if this variable appears in the program for the first time, then you allocate it to a memory address starting from address 16 onward. If you see this value popping up later in the program, you simply look up the value that you assigned to it before, and then what remains is an at decimal value instruction, which we already know how to handle. So this is how you handle symbols that represent variables. Now, I think that you will agree with me that handling all these different kinds of symbols is a major headache. And what can we possibly do to make this task I think that you will agree with me that handling all these different kinds of symbols is a major headache. And what can we possibly do to make this task simpler? Well, exactly for this reason, computer scientists have invented an artifact called symbol table. The symbol table is a very simple and powerful data structure that enables you to store and use symbol value pairs. And I can populate the table with as many symbol value pairs as I please. So when I write an assembler, I construct such an empty symbol table, and then I begin to populate it with all the symbols that I encounter in the program that I'm supposed to translate. And that's also how I'm going to explain to you the structure and the use of a symbol table. I'm going to do it constructively. I'm going to describe how we actually build a symbol table in order to deal with the example that we see here. And by the way, the same will hold for any other hack program that you will see in the future. So how do you create this symbol table? Well, the first thing that you do is you construct an empty symbol table, and then you populate it with all the predefined symbols which are specified in the language. So in the case of the hack assembly language, we have 23 such pairs. You simply add them up to the table one by one. And you do this, by the way, before you even touch the source program and before you start any translation. That's how you initialize the symbol table. Now, what do you do next? The next thing that you do is you march through the entire text file that constitutes your source assembly program. And the only thing that you do is you look for label declarations. You look for lines of code that begins with left parentheses. Once you have such line of code, you know that if the code was well written, if it contains no error, it must be the beginning of a label declaration. Now, as you do this, you also keep track of how many lines you read so far, And as I explained previously, you count only real instructions, skipping label declarations and white space. So once you do this, if you have this count in mind, when you encounter loop, for example, you should know that loop corresponds to 4. And then you go on, you ignore everything else until you hit the next label declaration, which is stop. And then you consult your counter. You see that stop corresponds to 18, and so on and so forth. Based on this scanning, you can continue to build the symbol table. And at the end of this process, you have added to the symbol table all the symbols that represent go-to destinations in your program, label symbols. Now, we call this process first pass. So the assembler that we're going to develop is going to be a 2-pass assembly process. In the first pass, we extract from the program all the label symbols. And in the second pass, which I'm going to discuss next, we're going to extract all the variable symbols. So here's what we do in the next pass. Once we finish the first pass, we start once again to scan the entire program from beginning to end. And whenever we see a label, or I'm sorry, whenever we see a symbol which does not appear in the symbol table, we know that it's a variable. So we add it to the table, and we assign to it the values 16, 17, 18, 19, and so on for as many variables as you have in the program. And when we encounter these variables later on in the program, we always look them up in the symbol table. If we find them in the symbol table, well, they are declared already and we can use them. If we don't find them, we can conclude that it's a new variable and we simply add it to the symbol table. That's the basic logic of constructing and utilizing. If we find them in the symbol table, well, they are declared already and we can use them. If we don't find them, we can conclude that it's a new variable and we simply add it to the symbol table. That's the basic logic of constructing and utilizing a symbol table. So how do you actually use it? Well, to resolve a symbol, you look it up. You look it up in the table, you extract or retrieve its value, put it into the instruction, and what you get is the meaning of this symbol according to the symbol table. Now, before we go on, I'd like to emphasize that the symbol table is some sort of an auxiliary data structure that the assembler needs in order to carry out the translation process. Once we finish the translation process, we can throw away the symbol table. We don't need it anymore. So we maintain it as long as the assembler is processing the program, and then we can toss it away. All right, so with that in mind, we can now describe the overall assembly process. We have reached to a point where we can actually lay out the algorithm for according to which the assembler can be developed. So here we go. First of all, we do some initialization. We construct an empty symbol table, and we get ready to process the input file. We add the predefined symbols to the symbol table, and then we go to work. We do a first pass. We go through the entire input file, and we look up we search for instructions that begin with the left parentheses, and we add the pairs XXX address to the symbol table as we go along. Then we do a second pass. In the second pass, we take care of the variable declarations, as I explained earlier. And at the same time, if we have an instruction which is a C instruction, we simply translate it into binary code. And if we have another at instruction which deals with a variable that has been declared previously, we look up the table, we replace the values, and so on. We take the binary code that we generated, we write it into the output file, and that's it. We have completed translating the program from symbolic to binary. Now, I have intentionally, I didn't read all the details of this algorithm because I discussed them in various different ways in the previous units and in this unit. So you're welcome to stop the video, consult this algorithm. them and convince yourself that it actually delivers the required translation. Them in various different ways in the previous units and in this unit. So you're welcome to stop the video, consult this algorithm, and convince yourself that it actually delivers the required translation task. So if you do all this, and if you actually implement it in some programming language or on a piece of paper if you want, or you can teach a human being to be an assembler if you want. If you do all of the above, you have accomplished the task of actually translating heck symbolic code into heck binary code. And that's the end of developing our assembler. In the next units, we're going to talk about actually building such an assembler using a programming language like Java or Python. Or if you're not a programmer, or if you don't have a previous knowledge of programming, we will also give you an option to develop an assembler without using a programming language. So stay tuned, and we'll discuss this in the subsequent units.
In this unit, we're going to describe our proposed architecture for an assembler. You've already seen the basic algorithms, the basic logic of what an assembler needs to do, but now we need to translate that into a real program and think about its architecture. Now, the truth is an assembler is a pretty simple program, and those of you who've already had significant programming experience can probably ignore this unit very safely and just go ahead and write the assembler. For those of you that have slightly less experience programming, you may want to look and remember our suggestions for a reasonable architecture, reasonable components of an assembler. Again, this is only a recommendation. You may want to look at our recommendation and then do whatever you feel most comfortable with. Our recommendation and then do whatever you feel most comfortable with. So let us see what are the types of modules that probably will be useful when we write an assembler, the type of operations that certainly need to be done. Well, 3 of them can be very easily identified, so let's talk about them. One of them is basically the parser, something that is able to read a file and get the different commands in it and breaks them into parts. That's the first part, reading and parsing command. You will need to do that. That's one thing. Another part of the code probably will have to actually understand how you convert a mnemonic, an assembly language command, or part of an assembly language command, into actual code. So that will have to understand the mapping, and that's another part that will need to be done somewhere probably in your assembler. And of course, there's another part that will need to be able to handle symbols, the symbol table itself. So let's talk a bit about these 3 different components, and once we talk about them, you'll see that the rest of the program, using these different components, which we think about as classes, and writing the complete program, there's not much left to be done. So let's start with the first part, reading and parsing command. The most important thing that we have to think about, what we don't need to worry in this part. So the whole point of the parser, of the component that reads and parses command, is it only needs to be able to read the input and break it into its parts. It doesn't need to understand anything. It doesn't need to understand what the commands mean. It doesn't need to understand how they're translated to machine language. It doesn't need to understand the symbols or their addresses. The only thing it needs to understand is the format of the input language and how it breaks into different components. So let us now see what are the different things, what are the different actions that it does need to worry about. So let us see what are the things it does need to do. Well, first of all, it needs to be able to read a file with a given name. So it needs to start being able to start reading a file. So in particular, for example, you may want, if you implement it as a class in some programming language, you may want a constructor to actually be able to accept a file name and then open the file for reading. So you will need to know how to handle text files, how to read text files in the language that you're implementing the assembler in. The second thing is, once you've started reading a file, you should be able to every time get the next command in the file. So getting the next command, if you look at it, what does it mean in terms of methods, operations that this part will have to do? Well, you'll probably first have to know whether you finished the file already. Are there more commands, or have you reached the end of the file? And then you'll need to be able to read into some kind of line, into some kind of string, the next command in the file. So the kind of thing, so what that entails is basically you will need some kind of string capability.
So they say you didn't need previous experience on anything to do this course, but I think you need to know some basic programming, right? Yeah. Anyway, the course is so good. So, yeah.
string handling capability, and you will need to know how to read line by line or something like that in your language. The third thing you will have to know how to do is to basically break the command that you've just read into its components. First of all, you need to know what kind of command is it. In our language, we have A commands and we have C commands, and also there are pseudo commands, if you wish, that define labels. These are not really commands in the sense of being translated to machine language, but for our assembler, it will have to basically know that here we have a label definition, so we can handle it. So that will be another third, if you wish, pseudo command that our assembler will have to know. Once we know that, we will probably want to give the rest of the program easy access to the different parts of the command. So for example, in assignment command, we'll probably want to give access to the destination part of the command, to the computation part of the command, and to the jump part of the command. Similarly, in a label or an A command, we'll just want to give our user access to the actual string, which may be a symbol and maybe an actual number that provides it. For example, the following set of methods, if you wish, in a Java or C-like in a Java-like language, probably would give you this type of access. But of course, the whole point, the important thing is that you get the pieces of information separately and in any way that you wish that one wants to provide them. The next thing that we have to do is translate each one of the components of the command into the actual machine code, into the binary code. Now, recall that in the specification of the language, basically, we have each part of the assembly language command has a separate part inside the bits of the machine language destination part. So move into the third part that we've already identified. That's very, very simple, and most translating it will probably want that piece a little bit in the program, new variable, and so on. It's very simple. You read you read a command from the input. That's basically a simple piece of code left to right after we have.
So in this unit, we finally come to a point in which we describe how to develop Project 6, which is implementing the assembler. And we wish to remind you that we have two options at this stage. If you want to write a program that actually implements an assembler using a programming language, you're welcome to listen carefully to this unit and use the guidelines that we provide to actually develop this program. If you don't have a programming background, then there's another unit that describes an equivalent project that write a program that actually
Oh, I was fucking wrong. Yeah, you didn't need, you don't need to know a computer language to do this project, because you can do it manually. Yeah, and they have a video here, so that was my bad.
implement an assembler using a programming language, you're welcome to listen carefully to this unit and use the guidelines that we provide to actually develop this program. If you don't have a programming background, then there's another unit that describes an equivalent project that implements an assembler without actually writing code. But I think that every one of you, even if you don't write the assembler using a programming language, it may pay off to listen to this unit and see an example of how to put together, how to carry out a complex software development project. So another unit that describes an equivalent project that implements an assembler without actually writing code. But I think that every one of you, even if you don't write the assembler using a programming language, it may pay off to listen to this unit and see an example of how to put together, how to carry out a complex software development project. So without further ado, we have to develop a hack assembler, and here's the contract. We decided that we will call our assembler hack assembler. This is an arbitrary decision, and this program should translate hack assembly programs that are written in symbolic hack code into executable hack binary code. And we assume that the source program is written in or supplied in a file, a text file called somename.asm. And given that this is the input that you have to operate on, your hack assembler program should generate a new file called the same name as the input file, .hack, so different extension. And once you create this file, we should be able to take this file, put it into the hack computer, and actually execute it. Now, we're making a big assumption, which is that the XXX, that the supplied input file, is error-free. So we don't have any programming syntax errors in this file. And in the last unit of this week, we'll talk about whether or not this assumption makes sense. So With all that in mind, you have to develop an assembler that follows this contract. And just for the sake of the argument, let's assume that you did it in Java, although you can do it in any other high-level language. If you did it in Java and you want to actually use the assembler, then we assume that you operate in some shell environment and you type Java, the name of the Java virtual machine. You provide the name assembler that you want to hit enter. Well, the binary code normally do, right? You write a program, make some corrections to the file. Now, how do we do it? Well, once again, you are welcome to write your architecture in any high-level language that you please. And yet, we recommend that you follow a certain software architecture. And we described this architecture in the previous unit, so I don't want to spend too much time talking about it, but I just want to remind you that the architecture that we propose consists of 4 different software modules. Each of these modules should be a standalone software module that can also be unit tested in isolation from the other modules. So we need a parser that unpacks each instruction into its underlying fields. We need a module called code that actually translates the symbolic fields, the mnemonics, into its corresponding binary value. And by the way, I should say it more precisely. It's not that the module translates. The module has a set of methods that are used to carry out this translation. We need a symbol table module that contains a set of methods that manage and create and manage a symbol table. And finally, we need a main module which actually drives the show. And it opens the input file, it creates an output file, and actually goes through the entire translation process by calling methods from the previously described modules. This main module will probably be named the heck assembler or something like that, depending on the language that you will end up using. So this is the proposed architecture that we recommend that you use in order to develop the assembler. Now, how should you actually go about it? How should you actually do the implementation? Well, we recommend that you follow what is sometimes called a staged development. We want you to develop the assembler in stages. So first of all, as I described in previous units, we want you to write a basic assembler that can handle programs or heck assembly programs that contain no symbols. Once you write this assembler, we want you to actually test it in isolation. That is, test it before you move on and do other things in this project. Once this basic assembler works to your satisfaction, you can go on and develop the symbol table module that can also be tested, and you should verify that you can create a symbol table and manage it in isolation from the other pieces of the project. Finally, once you have these two abilities in place, you can put them together and create an assembler that can actually translate any given assembly program. So this is yet another example of divide and conquer. You take a complex task, you split it into more manageable tasks, and complete and unit test each one of them in isolation. Now, in order to carry out this unit testing, we provide a set of 7 test programs that you are welcome to use in order to make sure that your assembler is actually working. Now, the first program, called add.asm, is very simple, and it's provided in one flavor only. Every one of the next 3 programs is supplied in 2 different versions, with symbols and without symbols. So the without symbol version of each program has capital L suffix, which stands for less symbols, max, less symbols, rectangle, less symbols, and so on. And in the next few slides, I'm going to talk about each of these programs in isolation. And that's exactly what you should also do in your project. You should test your assembler on each of these programs in different stages of development, and this will help you once again manage the process in a good way. All right, so here's the add program. The add program is a very simple hack language. It contains no symbols. It's just a bunch of a few A and C instructions, and it is designed to verify that your assembler can handle whitespace and instructions. That's it. Now, when you look at this program, you probably tell yourself that this is a very limited test, right? Because, well, for one thing, we didn't even test all the possible whitespace options, because we also have inline comments that we don't see in this program. And indeed, we don't claim that we provide programs that amount to an exhaustive testing of your assembler. It's just a very basic test, and you are welcome and encouraged to take this program, add.asm, and maybe make it more complicated. Add more comments, add more whitespace, add more instructions if you want, and just make sure that your assembler can handle these kinds of programs, simple programs, without any problems. So once again, the programs that we provide is just a minimum that you're welcome to extend with your own testing as well. All right, so this is the add program. The next program is called max, and as you can see from the documentation, it is designed to compute the maximum of 2 values. This is really not interesting at all from a translator's perspective. The translator has no idea what the program is trying to do. The translator is interested only in the syntax, but I'm saying it because I want you to know what is going on here. So this is the max program, and here is another version of this program without labels. So without symbols. And so the only difference between these two programs is that in the second program, we replaced every symbol with its numeric meaning. And once again, once you write your basic assembler, you should test it on max_L. And only later, when you add the ability to handle symbols, you should test your assembler on max_ASM. In a very similar fashion, we also provide a program called Rectangle that draws a rectangle on the screen, as we see here in this snapshot from the CPU emulator. So here's the code of the Rectangle program. Once again, we see that we supply two different versions of the same program. On the left-hand side, you see the full-blown version with symbols. On the right-hand side, you see the same program without symbols. We basically replaced every symbol with its numeric meaning. And once again, when you write your basic assembler, you should test it on Rectangle L first, and only later, when you write the full-blown assembler, you test it on Rectangle.asm. The last program that we provide is called Pong, and this is quite an elaborate program. It's a program that implements a Pong game, and the simplest way to describe it is to just give you a demo of how it works in the CPU emulator. So that's what we'll do next. Here we are in the CPU emulator, and we would like to demonstrate running a Pong game in the CPU emulator. So we go ahead and load the Pong program. So let us go to projects, and within projects we go to project 6, and we see that we have a folder called Pong. Open it. And we see that, as usual, in this project, we have two versions of the same program named Pong.asm and Pong-symbols.asm. Now, in the CPU emulator level, it doesn't really matter if you load into it a program with or without symbols, because the CPU emulator is going to resolve the symbols into physical addresses on the fly. In other words, the CPU emulator has a built-in assembler in it. And when you load a symbolic program into the ROM, which, by the way, is something that you cannot really do. We can do it only because it's an emulator. So once again, it translates everything into binary code. And to prove it, let us do that. Let's select this version of the program and load it into the ROM. And I see that I get a symbolic program, but there are no symbolic labels in it. All the symbolic labels, like, this probably has been at R0, and it was translated into at 3. So, and once again, this is just, for illustration purposes, because in reality, the program looks, excuse me, I think I have to do it here. Yeah, in reality, the program looks like this, but then obviously it's very difficult to follow it. So in the simulator level, we allow looking at the program both symbolically as well as numerically. All right, so this is a program that implements a simple Pong game, and it's quite a huge program. If you scroll, downstream, you will see that this program is, lo and behold, it is something like, let's see, something like 27,000 lines of code, which is a lot, right? But it's a little bit deceiving, because the program itself, the Pong logic, the logic of the Pong game, is much shorter. It's only maybe, I don't exactly remember, something like 200 lines of high-level language code. But by the time you translate this code into binary code, and now I'm talking about the compiler, translating from high-level language into assembly, then you get, many more lines of code, but still you don't get so many lines of code. The reason we have so much code here is because what you see here is not only an implementation of the Pong game, but also an implementation of the entire operating system that enables us to control the screen, the keyboard, and mathematics operations, and numerous other things that are needed when you implement and run high-level language programs. So once again, just to summarize, it's important to note that the code that we see here was originally written in the Jack high-level language, and then it was translated by a Jack compiler into eventually into the code that you see here. So this code was not written by a human being; it was written by a compiler. And of course, this whole business of writing high-level programs, writing compilers and operating systems and so on, are not covered in Nando Tetris Part 1, but rather they are covered in Nando Tetris Part 2. And yet, when you write an assembler, all this information is completely irrelevant. What you have is a file that consists of numerous lines of symbolic code, and you simply have to translate it into binary code. All right, so having said all that, let us try to run the program. So I click the fast forward, so to speak, and there seems to be a lot of action going on, but nothing appears on the screen. I'm a bit disappointed, because I expected to play a Pong game, and instead I see something that looks like a program executing, but once again, nothing is really happening. And indeed, you have to realize that what is happening here is the execution of a lot of setup code. The operating system is initializing all sorts of data structures, and all sorts of drivers are loaded, and so on and so forth. And it will take a while before the programmer's code proper will actually start running. So if we lose our patience, as I'm sure that every one of you has done already, we can stop this processing. We can rewind everything if we want, and we can tell the emulator that we don't want to see the program flow, and we do it by clicking this control here, the no animation. Now what we mean here is no code or execution animation. So let's do this and then run the program again, and hopefully we'll get to see some Pong action. All right, and hallelujah, there's a Pong game going on. That's quite amazing. Okay, so I'm playing Pong now. I'm not very good at it. Oh dear. And let me try another game. All right, maybe I'll make some improvement now. Wait, I have to do this. Okay, playing Pong. Let's see if I'm any better than before. Oh, hallelujah, I got a score of 2, 3. That's my world record so far. And 4, very impressive. And game over. So what you saw here is a Pong game in progress. I'm always excited to see programs like this working on the Hack computer, because this is a program that was written by us in Jack. It was compiled using a compiler that we wrote, and then the executable code could run on a computer that we actually built, or a computer that you actually built throughout this course. So this is, I think, very, very satisfying. So this has been a demo of a Pong game. You're welcome to play Pong on your own computer using the CPU emulator, which is stored in your Nando Tetris tools folder. And once again, I want to emphasize that as far as the assembler writer is concerned, all this story about Pong playing and so on, it's a very nice background story, but has no relevance whatsoever to writing an assembler. An assembler could not care less if it has to translate 12 instructions or 12,000 instructions. It's a computer program. It will process, whatever file we give it to process, and that's it. So I hope you enjoyed playing Pong with our Pong game, and it's time to open the black box and look at the Pong code. So here's the beginning of the Pong.asm program that we also supply as one of the test programs that you have to process, that your assembler has to process. I'd like to make some observations about this Pong.asm program because it's quite different in some respects from the previous programs that we saw in this project. First of all, the code of Pong was originally written in a language called Jack. Jack is a Java-like simple object-based language that we introduced in the second part of this course, in NAND to Tetris Part 2. And in NAND to Tetris Part 2, we introduce this language, and then we write a compiler that translates from this language all the way down to heck assembly code. And so what you see here is the result of this translation. So writing this compiler, and there's also a virtual machine in the middle that I don't have time to talk about. Writing these software layers is quite an elaborate undertaking, but we do it in a very similar style to what we did in this course. We do it one step at a time, and this is done in the second part of the course. The result of all this translation effort is the ASM program that you see in front of you. So the special thing about this program is that it was automatically generated by the compiler and by the virtual machine. The resulting code is about 28,000 instructions long. If you wonder why it's so long, it is because it also includes the Jack operating system. And the operating system is another thing that we develop in the second part of NAND to Tetris course. And taken together, we have an assembly language program. And if you translate it into binary code, then bingo, you have something that causes your computer to play Pong. And so we thought that it's important that as part of this project, we will also translate a so-called industrial strength program, and Pong is one such program. Now, when you look at this code, if you explore it, and we recommend that you look at it at least briefly. You don't have to understand what's going on here. It's very difficult to understand code just from looking at its the assembly version of this code. But you will realize that first of all, we don't have any white space, and that is because all the white space was lost in translation. And then you will see in this code all sorts of strange things. For example, you see some strange addresses like 256. Where does this 256 come from? Well, it comes from the way our virtual machine is implemented. Now, you may ask yourself, what is a virtual machine? Well, to find out, you have to take the second part of the course. You also see all sorts of strange labels, like for example, end underline eq. Where did this end eq come from? Well, this was generated by the compiler automatically when it translated the Jack code that was written by the programmer. And you also see some all sorts of predefined symbols that we haven't seen before, like SP. What is SP? Well, SP stands for a stack pointer, and once again, this is something that we discuss in the second part of the course. So when you look at this code, it's a little bit like reading genetic code, DNA. You have all sorts of strange things that were created by previous generations, so to speak. And indeed, the code that you see here was created by several layers of evolution. It's not exactly evolution, but we have a compiler that added some stuff to the code. We have a virtual machine that added some stuff to the code. And finally, you have something which becomes somewhat cryptic, but you can handle it to your assembler, and the assembler will translate it into machine code. And then finally, we'll have something that actually runs on your heck computer. Okay, so this is a long explanation of the Pong.asm program. As far as your assembler is concerned, all this explanation is irrelevant. It just has to take this file and translate it into binary code. So how should you test, the results of your work? Well, first of all, you have to use your assembler to generate heck programs written in binary code, and then you should test these programs and make sure that they actually do what they're supposed to do. So one way to do it is to invoke the supplied hardware simulator, load into it the built-in heck computer chip or the chip that you wrote, doesn't matter, although we recommend that you use the built-in chip to avoid the errors, and then load into this chip the heck code and run it. That's one testing option. Another testing option is to do the same, but use the CPU emulator instead of the hardware simulator. This will be a more user-friendly way to carry out this test. And finally, there is the option of choice, what we recommend that you actually do. We provide a working assembler, which is available to you on your personal computer if you've downloaded our software suite. Our assembler is called assembler, quite simply, and you can use our assembler to translate any one of the supplied ASM programs, and then you can compare the code that our assembler generated to the code that your assembler has generated. If the two codes are the same, then you know that your assembler is at least as good as ours, maybe better. Okay? So we do recommend that you use this third option in order to test your work, and here's how you actually do it. What we see here is a snapshot of the assembler that we supply in the course website, actually in the NAND to Tetris website. So you invoke this program called assembler. This nice window pops up, and then you can load into the assembler the ASM program, which you see here in the left pane. Then you will click a button, and our assembler will translate the symbolic code into binary code, and you see the resulting binary code in the center pane in this snapshot. Then you have an option to load into this program what we call a compare file. And the compare file is the heck program that was generated by your assembler. So once you do this, the program will not only load the compare file, it will also compare the two files, and then you will get a nice message saying that the comparison was successful, or a somewhat nasty message saying that the comparison was not successful, which means that your assembler produces code which is different from the code that our assembler produces. In which case, something is probably wrong in your assembler, and you have to test and fix it. Okay, so this is the recommended way to make sort of the final test that your assembler actually works. This is the source file, this is the heck file produced by our assembler, and this is the heck file produced by your assembler. So this basically sums up what you have to do. All the resources that you need are available in the NAND to Tetris org website, and the website describes the supplied files. There's no need to download anything, because if you downloaded the software suite at the beginning of the course, then all the files that you need for this project are available on your personal computer in the project/06 directory. And there's another set of resources that you might find useful, like the supplied assembler, the supplied CPU emulator, a tutorial, a proposed assembler API, and so on. All these things are available in the website, and you're welcome to use and consult them. So this has been the unit that gave you hopefully all the information that you need in order to build the assembler on your own. And the next unit will sum up everything that we did in this week. Welcome to the perspective unit of week 6, which is also the last week in the NAND to Tetris course. And there's 7 questions that come to mind about what we did during this week, which was mostly writing an assembler. And the first question that I'd like to discuss is the following one. Can you possibly improve the symbolic hack language without changing the binary code or the machine language, which is underlying the symbolic level? So indeed, we have 2 layers of expression here. We have the symbolic level, and we have the binary code that lies below it, if you will. And the assembler bridges this difference. And indeed, we can take this level, the symbolic level, and make it more user-friendly or more programmer-friendly. And there are various ways to do it. And in order to explain them, I will go to the board and show you some examples. So how can we make the hex symbolic language more programmer-friendly? Well, what we can do is introduce the notions of macro assemblers and macro commands. So let me say a few words about this added layer of abstraction. Let's take a typical operation like loading the D register with a value of some memory register. It is quite natural to think about a command that looks like this: D equals M, let's say at 100, okay? Which means go to register number 100, take its contents, and put it in the D register. This would be a natural thing to write, and yet the standard hack language does not feature such a command. So what I can do is I can take a command like this and translate it into 2 valid commands in the hack language, which will be at 100 and D equals M. Okay, so this is an example of what is sometimes called a macro command, and I can decide that whenever I write this command, I actually mean that I want these 2 commands to get executed. Likewise, think about jump instructions. For example, it will be very natural to say something like jump to this particular label, but once again, in the hack language, such an instruction is not permitted. So instead, I can expect this instruction to be translated into 2 instructions, which will be at loop and followed by a standard jump commands. So these are macro instructions, these are actual instructions, and in order to close this gap, I have to do something to my assembler. I have to extend the assembler and write it in such a way that whenever it encounters a command like this, it translates it into 2 machine language commands rather than a single one, which is what we normally did in the standard assembler. One question that often comes up when students work on assemblers is that, will I ever have to use an assembler outside school? Well, Noam, what do you think?
Well, the answer is exactly the same answer we gave to the question, will we ever need to use machine language, that we gave in week 4? Very, very rarely. Most of the time, people write in high-level languages and do not worry about the machine language. When they do worry about the machine language, of course, they will do it in assembly language, and thus they will need to use an assembler. But this is very rare, only in the special cases where performance is of utmost criticality. Now, in these cases, sometimes they will only want to focus on a very small part of the program and do it in assembly language, and do the rest in a high-level language. For example, C compilers allow you to do this kind of combination, to write most of your program in the C language, and in it embed a few commands in assembly. So the assembler is sort of part of the C language compiler, and allows you to deal with very specific points of the program that you want to extremely optimize and write them in assembly language. Beyond that, you will probably not worry that much or at all about assemblers or assembly language programming.
Now, this course is about building computers, and we had the tremendous luxury of using other computers in order to build the hack computer. And in particular, when we wrote the assembler, we wrote it using a high-level language like Java or Python or whatever language students have chosen to use when they wrote the assembler. Those of you who actually programmed the assembler, once again, used high-level language to do it. So the question is, historically, what happened when the first computers were designed, when you didn't have this tremendous luxury? How was the first assembler actually written? So, Noam, you want to take this question?
So this is a very mind-bending question. Before I answer it, I would like to re-emphasize again that conceptually it only holds for the first time you write an assembler. In reality, most of the time there are already computers, and usually you use the computers that you already have with a high-level language that you already have to write code and assemblers and basic functionality for the new computer. Now, given that we are still talking about the first computer conceptually in history, how was that done? Well, in this course you also saw that. So remember that the students that are not programmers in this course simply had to compile something by hand. They got an assembly language program and needed to translate it one command at a time into machine language. That you can always do. So conceptually, what you can really do is you start to write a high-level assembler. You write an assembler in a high-level language and translate it by hand for the first time only into a machine language of your computer. Once you finish this translation, which is extremely time-consuming, extremely annoying to do, but only needs to be done once conceptually, then now you already have a machine language that runs your compiler or your assembler or any high-level help that you want, and then you can keep on using it for the rest of time.
So, folks, that's it. We're done building the computer. We started with NAND gates 6 weeks ago, and we worked our way through several different types of chips. We built an ALU, a CPU, a memory system. We put everything together, and we got a fully functioning computer. We added to it an assembler, so we can actually program this computer in a relatively friendly language, and that's it. We have a computer that can run any program that comes to your mind, including, of course, Tetris. So I'm very happy with this computer. Noam, are you happy with it also?
Well, Shimon, part of the motivation for this course was demystifying computers, leaving the student with a clear understanding what goes on beyond this amazing beast called the computer. I think we've only partially done that. We basically understand, I think the students now understand how the hardware works. What is still quite mystifying, I think, to almost anyone that looks at computers is all the different software layers that that exist above it. When you actually use a computer, you talk with an operating system, you write in a high-level programming language. It's very far from writing programs in this little assembler that we've already shown. It would be nice, wouldn't it, if we actually had a second part of the course that actually does talk about all these software layers that are above the hardware level, that explain, again, in the same manner that we've explained so far, how you can actually construct the different software layers, the compiler and what is required for it, the operating system, and getting to a level where the software hierarchy is demystified like we've demystified the hardware hierarchy so far.
So thank you, Noam, for this criticism. And luckily, I'm just reminded that we actually solved this problem also because we have a complete second part of this course in which we do precisely what Noam just described. And so in the second part of the course, we start with the hardware that you wrote or developed in this course, and we add the software hierarchy that needs to operate on top of it. And then we end up with a language which is very similar to object-oriented modern programming languages, and then you can really write programs like Tetris and anything that you want on this computer and see it get execute on the hardware that you actually built in the first part of the course. Now, how should you go about doing this? Well, there are two ways to do it. First of all, you can get a copy of this book, which gives you everything that you need in order to develop the software hierarchy of the computer. Just like we did in this course, the software hierarchy will be divided into 6 or 7 different projects that you work on each week of the course. So that's one way of doing it, do it yourself. And the second way of doing it is just waiting until the second part of NAND to Tetris will be available on Coursera, and then you can just take the course, just like you took this one, and complete this second piece, which is still missing. So with this, folks, the course is practically over. We hope that you enjoyed the ride. We want to thank you for the time and effort that you invested into taking this course, and we hope very much to see you in the second part of NAND to Tetris. So with that, bye! Welcome to the perspective unit of week 6, which is also the last.
Ya, ¿en qué lenguaje lo programamos? Supongo que en Ruby, ¿no? Ya, primero voy a comitear esto. Listo. Entonces, vamos a crear un proyecto. ¿Y cómo hacemos esto?
La pieza de pizza, Mora.
A ver, ¿funcionará esto? Sí. Ya. Entonces aquí, pero mientras vamos a cerrar esto. A ver. Tenemos estos dos. Bla, 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 bla. Entonces, copiar esto. Entonces, terminal. CD. No sé si era CD. Ya, acá. Y vamos a cerrar esto. Tenemos code. The word operation with the file system for reference you recommend moving the workspace to the Linux home. Yeah, but I know. What? ¿Por qué que parece como? Qué interesante. Lol. Don't like it. No quiero perder mis commits. Vamos a hacer... ya sé qué vamos a hacer. Vamos a ignorarlo. Lo primero, aquí. Quiere hacer esto. Outputs. Aquí. Sí. 06. Ah, ya sé. Ya sé. Vamos a ver el code aquí. Vamos a crear un repositorio. Aquí GitHub. Branch main set double drag, yeah. Yep. Now we can do C. Ahora sí. Acá. ¿Cómo hacemos? Main.rb. Ruby. Ya. Entonces, ¿cómo están estos programitas? A ver. 0, bla, bla, bla. Ya. ¿Dónde está el proyecto? Quiero ver. La especificación del lenguaje, ¿no? ¿Será acá? Tan. Assembly to binary translation. Eso es todo lo que necesito. Ahora vamos a seguir la estructura que ellos plantean. Está aquí. ¿Cómo era?
Heck, I'm talking about it, but I just want to...
Tienen parser, call, symbol table. ¿Cómo es esto? Tienes parser, call, symbol table más y main. Ya hay que hacer cada uno. Unpacks each instructions. Underline fields. Code. Translate each field. Fields to binary. What is this? Maintains symbol values. Este es un orchestrator. Pero siento que aquí falta una abstracción, ¿verdad? ¿Quién es el que transforma los fields y los ordena? Interesante. Por ejemplo, este de aquí. Esto, ¿cómo se transforma? Ya. Destination está al final. Y comp, esto viene a ser las instrucciones del ALU. Si destination está al final, debe haber un intercambio de order, ¿no? Ahora esto se puede hacer, se puede llevar por code, va a terminar así, D plus A, y luego esto no se va a code. Okay, I'm not going to follow this structure. Es que esto va a tener dos responsabilidades. Uno de traducir ya parser. Porque también tenemos instrucciones del mismo lenguaje, ¿no? Por ejemplo, esto no va a ir en el symbol table. A menos que esto tenga dos métodos, ¿no? Translate translate symbols o y otro que sea translate symbol. No, fields. No hay fields. Yeah, I can do that. Code puede usar parser por debajo. Instructions into fields. sé. Ya, a ver, vamos a ver. Necesitas un instruction translator o assembler. Instruction translator. Luego, en la primera pasada va a haber un parser. Pero el parser debe encargarse de llenar el symbol table en first run y wait.
Ya va a cambiar, mi amor. ¿Ya vas a cambiar eso? Baby.
Que bota el parser. Retorna el symbol table. retorna una lista de instrucciones. Separadas en fields con un tipo. Ya, nada más. Recorre las instrucciones y se transforma a binario. Retorna el código en binario. Así será. Ya, eso está fácil. Entonces, primero vamos a crear el parser. El parser. Perdón. Sí. Class parser. What? Robocop. Ruby. Está. Tan, tan, tan.